The Milky Way is a barred spiral galaxy, approximately 13.6 billion years old. It formed not long after the Big Bang itself, when the universe was still in its infancy, making it one of the oldest structures in the cosmos, and a witness to billions of years of cosmic evolution. From edge to edge, the Milky Way stretches about 100,000 light-years in diameter. To grasp this scale, consider that light travels at 186,000 miles per second. In a single year, it covers nearly 6 trillion miles. Now multiply that distance by 100,000, and you begin to understand the vastness of our galactic home. Yet despite this enormous width, the Milky Way is remarkably thin, measuring only about 1,000 light-years from top to bottom. If the galaxy were the size of a dinner plate, its thickness would be no more than a sheet of paper. This disk-like structure is characteristic of spiral galaxies throughout the universe, a flattened rotating system held together by gravity. Inside this colossal disk live roughly 200 billion stars. Some burn bright and hot, radiating blue-white light across the cosmos. Others glow dim and cool, casting a faint red hue into the surrounding space. Some are newborn, freshly ignited from collapsing clouds of gas and dust. Others are ancient red giants, swollen and nearing the end of their lives, ready to shed their outer layers into space. Each star is a sun in its own right, and many host their own planetary systems orbiting around them, worlds we are only now beginning to discover and catalogue. Among this multitude of 200 billion suns is our own star, an ordinary yellow dwarf we call the Sun. It is neither the largest nor the brightest star in the galaxy, but it is ours, and it provides the energy that makes life possible on Earth. Without this unremarkable star, there would be no planets, no oceans, no forests, and no humanity. We owe our existence to this single point of light among billions. Our solar system is not stationary within the galaxy. It races through space at 515,000 miles per hour, orbiting the galactic center in a great cosmic dance. Even at this tremendous velocity, one complete orbit takes roughly 250 million years. This interval is sometimes called a galactic year, and it represents the time it takes for our solar system to make one full lap around the Milky Way. The last time our solar system occupied its current position in the galaxy, dinosaurs had not yet evolved on Earth. Trilobites still dominated the oceans, and life had not yet crawled onto dry land. The continents were arranged differently, and the climate was unrecognizable. In the 4.6 billion years since Earth formed, our planet has traveled around the galaxy only about 18 times. The entire span of human history, from the first civilizations in Mesopotamia and the Nile Valley to the present day, represents a mere fraction of a single orbit. Everything we have ever known, every empire that has risen and fallen, every discovery and invention has occurred in just one small arc of our journey around the galaxy. We are passengers on a cosmic journey that dwarfs all of recorded time. Where exactly do we sit within this spiral? Our solar system resides in a region called the Orion Cygnus Arm, sometimes referred to simply as the local arm. This is a minor spiral arm, a spur nestled between two of the Milky Way's major structures, the Perseus Arm and the Carina Sagittarius Arm. We are positioned approximately 26,000 light-years from the galactic center, roughly halfway between the core and the outer edge. This is a relatively calm neighborhood. The center of the galaxy is crowded violent, and flooded with intense radiation from densely packed stars and exotic phenomena. Millions of stars are crammed into a relatively small volume, their gravity pulling at each other. The outer edges are sparse and cold, with stars scattered thinly across vast distances, isolated and alone. Our location strikes a balance, a quiet zone where stars form steadily and planets can evolve in relative peace. This cosmic real estate may be one reason why life had the opportunity to arise and flourish on Earth. We live in what astronomers call the galactic habitable zone, a region where conditions are just right for complex chemistry and biology, where supernovae are rare enough not to sterilize planets, but common enough to enrich the interstellar medium with heavy elements. The name Milky Way comes from the galaxy's appearance in our night sky. When you look up on a dark, clear night, far from city lights and pollution, you see a faint band of light arcing overhead. To the naked eye, it resembles a river of milk spilled across the heavens. The ancient Greeks called it Galaxias Kyklos, meaning milky circle. The Romans named it Via Lactea, the Milky Way, the road of milk. Different cultures around the world gave it different names, each reflecting their own myths, legends, and stories. To some Native American tribes, it was a path of souls traveling to the afterlife. In Chinese mythology, it was a silver river separating two star-crossed lovers, Niu Lang and Xinu. In Hindu tradition, it was the celestial Ganges. To the Aboriginal peoples of Australia, it was a river in the sky. To others, it was the backbone of the night sky holding the heavens together. But all recognized the same phenomenon, a glowing ribbon stretching from horizon to horizon, offering a glimpse of our galaxy from the inside. We are looking at the Milky Way from within, seeing the combined light of billions of distant stars that make up the galactic disk. Every star you can see with your naked eye is part of our galaxy, a neighbor in our cosmic city. The Milky Way is far more than a static collection of stars frozen in space and time. It is a dynamic, living system with a rich and violent history and an uncertain future. It has collided with smaller galaxies in the past, absorbing them and growing larger with each merger, like a cosmic predator consuming its prey. Evidence of these ancient collisions can still be seen today in streams of stars that orbit the galaxy in strange patterns. It will collide again. Understanding the Milky Way helps us understand where we came from and where we are going as inhabitants of this vast cosmic structure. This is the foundation of our journey through the galaxy, a barred spiral galaxy, 13.6 billion years old, 100,000 light-years across, 1,000 light-years thick, home to 200 billion stars, and the birthplace of our solar system and our planet Earth. In the parts ahead, we will delve deeper into this galactic machine. We will explore its detailed structure and components, the precise location of our sun within it, the supermassive black hole lurking at its heart, its violent past filled with collisions and mergers, and its dramatic future as it hurtles toward another galaxy billions of years from now. But for now, we know the essentials. We know where we are. We know our place in this vast cosmic city of stars. And we are ready to go further into the depths of our cosmic home, the Milky Way galaxy, to understand the machine that gave us life. The Milky Way has 6 major components that work together to form the galaxy we call home. At its heart lies the galactic center, a region of incredible density and energy. Surrounding this core is the central bulge, a roughly spherical concentration of stars that bulges above and below the galactic plane. Beyond the bulge stretches the disk, a flattened rotating region where most of the galaxy's visible matter resides. Embedded within the disk are the spiral arms, sweeping structures that trace the galaxy's pinwheel shape. Enveloping everything in the halo, a vast spherical region containing ancient stars and mysterious dark matter. Together, these components create a complex, dynamic system that has evolved over billions of years. The central bulge is approximately 10,000 light-years wide and contains roughly 10 billion stars. Most of these stars are old, typically 7 billion years or older, making them among the most ancient objects in the galaxy. They are population 2 stars, relatively rich in heavy elements compared to the oldest stars, but still metal-poor by modern standards. The bulge has a distinctive peanut shape, a structure revealed by infrared observations that can peer through the obscuring dust of the galactic plane. This unusual shape likely resulted from gravitational interactions and dynamical instabilities that occurred early in the galaxy's history. The stars in the bulge glow with a reddish hue, the characteristic color of old red giant stars nearing the end of their lives. Unlike the disk, the bulge shows little active star formation today. Its stars formed long ago and now slowly orbit the galactic center on nearly radial paths, plunging in and out of the central regions. The disk contains most of the young stars, gas and dust in the Milky Way. It is a flattened, rotating region approximately 100,000 light-years across and about 1,000 light-years thick. The disk is not uniform but consists of 2 distinct regions, the thin disk and the thick disk. The thin disk is the primary site of star formation, rich in the interstellar medium of gas and dust that provides the raw material for new stars. It contains young, hot blue stars alongside older yellow stars like our Sun. The thick disk sits above and below the thin disk and contains older stars with intermediate properties between those of the thin disk and the halo. These thick disk stars orbit the galaxy on paths that carry them farther above and below the galactic plane, creating a more diffuse vertical distribution. The disk is not perfectly flat. Observations reveal that it is warped, bending up on one side and down on the other, like the brim of a hat someone sat on. This warping extends throughout the outer regions of the disk and may result from gravitational interactions with satellite galaxies or the dark matter halo. The disk also precesses, slowly wobbling like a spinning top that is starting to lose its momentum. This precession occurs over millions of years and reflects the complex gravitational forces acting on the galaxy. 4 main spiral arms sweep through the disk: the Perseus Arm, the Scutum Centaurus Arm, the Sagittarius Arm, and the local arm where our solar system resides. These arms are not solid structures but density waves, regions where stars, gas, and dust pile up temporarily as they orbit the galaxy at different speeds. The spiral arms contain higher concentrations of interstellar gas and dust than the galactic average, making them prime sites for star formation. Within the arms, massive clouds of molecular hydrogen collapse under their own gravity, fragmenting into clusters of newborn stars. These young hot stars shine brightly in blue and ultraviolet light, illuminating the spiral arms and making them visible across vast distances. The exact number and structure of the spiral arms remain subjects of active research, with some models suggesting two major arms and several minor spurs branching off from them. Surrounding the disk and bulge is the halo, a roughly spherical region that extends to at least 150,000 light-years from the galactic center. The halo contains very little gas, or dust, but is populated by ancient stars and globular clusters. These globular clusters are tightly bound spherical collections of hundreds of thousands to millions of stars, all born at roughly the same time from the same primordial cloud. The Milky Way hosts approximately 40 dwarf galaxies within its halo, small satellite galaxies that orbit our larger galaxy like moths around a flame. These dwarf galaxies are being slowly torn apart by the Milky Way's gravity, their stars stripped away and scattered into long streams that wind through the halo. The halo stars are predominantly population 2 stars, extremely old and deficient in heavy elements. They formed early in the universe when only hydrogen and helium were abundant, before generations of supernovae had enriched the cosmos with carbon, oxygen, iron, and other elements. Many halo stars orbit the galaxy at very high speeds relative to the Sun, earning them the name high-velocity stars. Beyond even the visible halo lies the dark matter halo, an enormous invisible structure that extends to at least 200,000 light-years from the galactic center and possibly much farther. This dark matter does not emit, absorb, or reflect light, making it completely invisible to telescopes. Yet its presence is undeniable. The rotation curve of the Milky Way, which measures how fast stars orbit at different distances from the center, reveals that the galaxy contains far more mass than we can see in stars, gas, and dust. This missing mass is dark matter, and it constitutes the majority of the galaxy's total mass. The dark matter halo plays a crucial role in the galaxy's gravitational dynamics, holding the visible components together and determining how the Milky Way interacts with neighboring galaxies. Understanding dark matter remains one of the greatest challenges in modern astronomy. The structure of the Milky Way is the product of billions of years of evolution. Each component tells part of the story of how our galaxy formed, grew, and changed over cosmic time. In the next part, we will zoom in on our specific location within this vast machine and explore how the Sun and Earth fit into the grand architecture we have just described. Earth lies approximately 26,000 light-years from the galactic center. This places us roughly halfway between the densely packed core and the sparse outer edges of the Milky Way's disk. The Sun orbits the galaxy every 230 million years, completing one full circuit around the galactic center at a velocity of 515,000 miles per hour. This orbital period, called a galactic year, means that in the entire 4.6 billion year history of our solar system, we have completed only about 20 orbits. The last time we occupied this exact position in the galaxy, the supercontinent Pangaea was just beginning to break apart on Earth. Dinosaurs were entering their age of dominance. Since then, we have travelled one complete lap around the galaxy, witnessing the rise and fall of countless species. The Sun sits near the edge of the local arm, also known as the Orion Cygnus Arm. This is a minor spiral arm, a spur connecting two of the galaxy's major arms. The Perseus arm lies outside our position, farther from the galactic center. The Carina Sagittarius arm lies inside, closer to the core. Our location in this minor arm places us in a relatively calm region of space. The major spiral arms are sites of intense star formation where massive young stars live fast and die young in spectacular supernova explosions. These explosions flood their surroundings with deadly radiation. By residing in a minor arm, the Sun avoids the worst of this cosmic violence, creating a safer environment for planets and potentially for life itself. Recent data from the Gaia spacecraft has revealed something unexpected about the Sun's journey through the galaxy. The Gaia mission, launched by the European Space Agency, has been mapping the positions and motions of more than 1 billion stars with unprecedented precision. This data revealed that the Sun is traveling on a 9,000 light-year-long wave of interstellar gas. This wave, called the Radcliffe Wave, extends above and below the galactic plane and contains many of the nearest star-forming regions. The Sun appears to be oscillating up and down through this wave as it orbits the galaxy. Every 33 million years, the Sun crosses the galactic plane, passing from above the midpoint to below it, or vice versa. This oscillation may expose Earth to varying levels of cosmic radiation and interstellar dust as we move through different regions of the galaxy. The solar system's orbital plane is tilted 63 degrees relative to the Milky Way's disk. This means the ecliptic, the plane in which Earth and the other planets orbit the Sun, is not aligned with the galactic plane. If you could stand on the surface of the Sun and look toward the galactic center, you would need to tilt your head significantly downward or upward to see the midplane of the galaxy. This tilt results from the complex gravitational interactions that shape the solar system during its formation 4.6 billion years ago. The cloud of gas and dust that collapsed to form the Sun and planets had its own angular momentum, independent of the galaxy's overall rotation. As a result, the solar system spins at an angle to the galaxy itself. Understanding our precise location within the Milky Way took centuries of careful observation and analysis. For most of human history, people had no idea we lived inside a galaxy at all. The ancient Greeks and Romans saw the Milky Way as a river of milk across the sky, but did not understand its true nature. Even as recently as the early 20th century, astronomers debated whether the Milky Way constituted the entire universe or whether other galaxies existed beyond it. The famous Great Debate of 1920 between astronomers Harlow Shapley and Heber Curtis centered on this question. Shapley argued that spiral nebulae were clouds within our galaxy, while Curtis correctly proposed they were distant island universes, separate galaxies millions of light years away. Our understanding advanced dramatically in the 1920s when Edwin Hubble used the newly constructed Mount Wilson telescope to observe individual stars in the Andromeda Nebula. He identified Cepheid variable stars whose brightness varies in a predictable pattern related to their intrinsic luminosity. By measuring their apparent brightness and comparing it to their true luminosity, Hubble calculated that Andromeda lay nearly 1 million light-years away, far beyond the boundaries of the Milky Way. This proved that spiral nebulae were indeed separate galaxies, and that the universe was vastly larger than previously thought. Determining our location within the Milky Way proved even more challenging. Unlike observers viewing a distant galaxy from outside, we must map our galaxy from within, like trying to draw a map of a forest while standing among the trees. Dust in the galactic plane blocks visible light, making it impossible to see the galactic center directly with optical telescopes. Radio waves and infrared light can penetrate this dust, revealing structures hidden from visible light observations. By mapping the distribution of neutral hydrogen gas using its characteristic 21-centimeter radio emission, astronomers gradually pieced together the spiral structure of the galaxy and located the Sun's position within it. The Gaia spacecraft represents the latest and most ambitious effort to map the Milky Way. Launched in 2013, Gaia measures the positions, distances, and motions of more than 1 billion stars across the galaxy. This data has revolutionized our understanding of galactic structure and dynamics. Gaia has revealed streams of stars torn from dwarf galaxies, mapped the warped and twisted shape of the disk, and traced the orbits of stars throughout the galaxy. Every new data release from Gaia brings fresh insights into the architecture and history of our cosmic home. Our location in the Milky Way is not a cosmic accident. It reflects the conditions necessary for complex chemistry and biology to develop. Too close to the galactic center, and planets would be bathed in radiation from supernovae and disrupted by close encounters with other stars. Too far toward the outer edges, and the interstellar medium would lack the heavy elements necessary to form rocky planets and organic molecules. We live in the galactic habitable zone, a region where conditions are just right for life. In the next part, we will journey to the very heart of the galaxy and explore the supermassive black hole that dominates the galactic center. The central black hole at the heart of the Milky Way is called Sagittarius A star. This designation comes from its location in the constellation Sagittarius and its status as a powerful radio source. Sagittarius A star has a mass of 4.3 million times that of our Sun. To put this in perspective, if you could somehow place 4,300,000 suns on a cosmic scale, their combined mass would equal that of this single black hole. This makes it a supermassive black hole, a class of objects found at the centers of most large galaxies. Despite its enormous mass, Sagittarius A star occupies a relatively small volume of space. Its diameter measures approximately 14.6 million miles, which equals about 23.5 million kilometers. This is roughly the distance from the Sun to the planet Mercury. An object with millions of solar masses compressed into such a small region creates gravitational fields so intense that not even light can escape once it crosses the event horizon surrounding Sagittarius. A star is a disk of gas that extends from 5 to 30 light-years outward from the black hole. This accretion disk consists of material that has been captured by the black hole's gravity, but has not yet fallen in. As gas spirals inward through the disk, it heats up due to friction and compression. The inner regions of the disk reach temperatures of millions of degrees, hot enough to emit X-rays. These X-rays allow astronomers to study the environment around the black hole, even though the black hole itself emits no light. The gas does not fall directly into the black hole, but instead orbits in gradually tightening spirals, losing energy through radiation and magnetic interactions. Eventually, after perhaps thousands of years of spiraling inward, the gas crosses the event horizon and disappears from the observable universe. The black hole emits X-rays due to the hot infalling gas. As matter accelerates toward the event horizon, it reaches speeds approaching the speed of light. At these velocities, Collisions between particles in the gas transfer tremendous amounts of kinetic energy into heat. The superheated gas glows brilliantly in X-rays, creating a luminous halo around the otherwise invisible black hole. Astronomers use X-ray telescopes in space, such as the Chandra X-ray Observatory, to study this high-energy emission. These observations reveal not only the presence of the black hole, but also details about how it feeds and grows over time. Sagittarius A star is relatively quiet compared to the supermassive black holes in other galaxies. Some galactic centers emit thousands of times more radiation, powered by massive inflows of gas and dust. Our black hole, by contrast, is on a starvation diet, accreting material at a slow rate. The first image of Sagittarius A star was captured in 2022 by the Event Horizon Telescope. This was a monumental achievement in observational astronomy. The Event Horizon Telescope is not a single instrument, but a global network of radio telescopes spread across the Earth. By combining observations from telescopes in locations ranging from Hawaii to Antarctica to Spain, astronomers created a virtual telescope the size of the entire planet. This technique, called very long baseline interferometry, provides the resolution necessary to image the immediate environment around a black hole 26,000 light-years away. The image shows a bright ring of emission surrounding a dark central region. The dark region is larger than the event horizon itself because it includes the photon sphere, a region where light can orbit the black hole before either escaping or falling in. The bright ring is emission from hot gas in the accretion disk, bent and distorted by the extreme curvature of spacetime near the black hole. The image of Sagittarius A star confirmed predictions made by Einstein's general theory of relativity more than a century ago. Einstein's equations describe how massive objects warp the fabric of spacetime, and they predict the existence of black holes as regions where this warping becomes infinite. For decades, these predictions remained theoretical, supported by indirect evidence but lacking direct visual confirmation. The Event Horizon Telescope images of Sagittarius A star and the supermassive black hole in the galaxy Messier 87 provided that confirmation. The shape, size, and brightness of the observed rings match theoretical predictions with remarkable precision. Studying Sagittarius A star helps astronomers understand not only black holes, but also the evolution of galaxies themselves. Almost every large galaxy appears to harbor a supermassive black hole at its center. The mass of the central black hole correlates with properties of the surrounding galaxy, such as the total mass of stars in the bulge. This correlation suggests that black holes and galaxies grow together, each influencing the other's evolution. When a black hole actively feeds, it can emit powerful jets of matter and energy that heat the surrounding gas and regulate star formation. This feedback mechanism may explain why the largest galaxies eventually stop forming new stars, their gas supplies depleted or heated by their central black holes. The environment near Sagittarius A star is one of the most extreme in the galaxy. Stars orbit the black hole at incredible speeds, their motions governed entirely by its gravitational pull. Astronomers have tracked individual stars orbiting Sagittarius A star, measuring their velocities and orbital periods. One star, designated S2, completes an orbit in just 16 years, reaching speeds of up to 5,000 kilometers per second at its closest approach. These orbital measurements allow astronomers to calculate the black hole's mass with high precision and to test general relativity in the strong field regime where Newtonian gravity fails completely. The discovery and study of Sagittarius A represents one of the great triumphs of modern astronomy. From early radio observations that detected a mysterious source at the galactic center to the recent direct imaging of its shadow, each advance has deepened our understanding of these enigmatic objects. Sagittarius A anchors the Milky Way, its gravity holding the central regions of the galaxy together. In the next part, we will explore the history of our galaxy, how it formed, how it has evolved through collisions and mergers, and how our sun came to be born in the aftermath of one such collision billions of years ago. The Milky Way formed from collapsing gas clouds, roughly 13.6 billion years ago, creating the first stars and the halo. In the early universe, only hydrogen and helium existed in significant quantities, the products of the Big Bang itself. Gravity pulled these primordial gases together into immense clouds that collapsed under their own weight. As the clouds collapsed, they fragmented into smaller regions that ignited nuclear fusion in their cores, becoming the first generation of stars. These population 3 stars, as astronomers call them, contained no heavy elements at all. They were massive, short-lived, and when they died in supernova explosions, they seeded the universe with the first heavy elements: carbon, oxygen, silicon, iron, and all the other elements necessary for planets and life. The oldest stars in the Milky Way's halo date back to this era, ancient survivors that have witnessed the entire history of our galaxy. Evidence of past collisions with smaller galaxies can be found throughout the Milky Way. Galaxies are not isolated islands, but members of groups and clusters that interact gravitationally over time. When a small galaxy passes too close to a larger one, tidal forces tear it apart, stripping away its stars and spreading them into long streams. The Milky Way has consumed dozens of smaller galaxies over billions of years, each collision leaving behind telltale signs. Gaia data shows streams of stars that orbit the galaxy in patterns completely different from the orderly rotation of the disk. These streams trace the orbits of disrupted dwarf galaxies, their stars now scattered across the halo like breadcrumbs marking a path. By analyzing the chemical composition and motion of these stars, astronomers can reconstruct the history of past mergers and identify which stars originally belonged to which galaxy. The Gaia spacecraft has revolutionized our understanding of the Milky Way's violent past. Launched in 2013, Gaia measures the positions, distances, and velocities of more than 1 billion stars with unprecedented precision. Each data release has revealed new structures and unexpected patterns. Gaia discovered that the Milky Way collided with a dwarf galaxy called Gaia Enceladus approximately 10 billion years ago. This collision was not a glancing blow, but a major merger that fundamentally altered the structure of the young Milky Way. The dwarf galaxy plunged through the disk, its stars scattered throughout the halo and inner galaxy. Many of the stars in the thick disk and inner halo originated in Gaia Enceladus, making them immigrants from another galaxy. This discovery rewrote our understanding of galactic evolution. Rather than growing smoothly over time, the Milky Way experienced violent episodes of growth through cannibalism. The Sagittarius dwarf galaxy has impacted the Milky Way several times, triggering star formation bursts. This small elliptical galaxy orbits the Milky Way on a path that carries it through the galactic disk. Each time it passes through, the gravitational interaction compresses gas clouds in the disk, triggering waves of star formation. The Sagittarius dwarf is currently in the process of being torn apart. Long streams of stars wrap around the Milky Way like ribbons, tracing its orbital path. Future passages will strip away more stars until eventually nothing remains of the original galaxy. The Sagittarius dwarf is not alone. The Milky Way's halo contains approximately 40 dwarf galaxies, most of them faint and difficult to detect. The largest are the Large Magellanic Cloud and the Small Magellanic Cloud, visible to the naked eye from the southern hemisphere. These two galaxies orbit the Milky Way and may eventually be consumed as well, adding their stars to our galaxy's growing population. Our Sun likely formed during one such burst 4.6 billion years ago. Analysis of isotopes in meteorites suggests that the solar system formed from a gas cloud enriched by a recent supernova explosion. The shockwave from that supernova may have triggered the collapse of the cloud, compressing it until it fragmented into the Sun and planets. This supernova could have been triggered by a collision with a satellite galaxy passing through the disk. If so, then we owe our existence not just to one galaxy, but to at least two, the Milky Way and whichever dwarf galaxy triggered the star formation burst that created our Sun. Every atom in your body heavier than helium was forged in the core of a star or in a supernova explosion. We are literally made of stardust, recycled stellar material that has passed through multiple generations of stars over billions of years. The Milky Way continues to evolve and change. Star formation proceeds in the spiral arms, where new stars are born from collapsing gas clouds. Old stars die, some quietly fading away as white dwarfs, others exploding as supernovae that enrich the interstellar medium with heavy elements. The galaxy rotates differentially, meaning different parts orbit at different speeds. This differential rotation winds up the spiral arms, making them tighter over time. Interactions with satellite galaxies perturb the disk, causing ripples and oscillations that propagate through the stellar distribution. The dark matter halo, though invisible, exerts gravitational influence that shapes the orbits of stars and satellites. Understanding the Milky Way's history helps astronomers understand galaxy evolution more broadly. The same processes that shaped our galaxy operate in galaxies throughout the universe. By studying the Milky Way in detail, we gain insights into how all galaxies form, grow, and evolve. The Milky Way serves as a laboratory for testing theories of galaxy formation and a benchmark against which to compare observations of distant galaxies seen as they were billions of years ago when the universe was young. Our location inside the galaxy, while it complicates mapping efforts, provides a unique perspective unavailable for any other galaxy. We can study individual stars in unprecedented detail, measuring their ages, compositions, and motions to reconstruct the galaxy's history, star by star. The story of the Milky Way is far from over. In the next part, we will look to the future and explore what awaits our galaxy in the billions of years to come, including its eventual collision with the Andromeda Galaxy and the fate of the solar system in that cosmic merger. The Milky Way is on a potential collision course with the Andromeda Galaxy in approximately 4 to 8 billion years, though groundbreaking research published in 2025 has dramatically challenged the long-held certainty of this event. Andromeda, also known as Messier 31, is the nearest large spiral galaxy to the Milky Way, located about 2.5 million light-years away. To put this distance in perspective, light from Andromeda takes 2.5 million years to reach Earth, meaning we see Andromeda not as it is today, but as it appeared when early human ancestors walked the Earth. Despite this enormous distance, Andromeda is racing toward us at more than 250,000 miles per hour, which equals roughly 400,000 kilometers per hour. For decades, astronomers believed this collision was inevitable, a cosmic fate written in the motions of galaxies. Studies conducted in 2012 using the Hubble Space Telescope and the Very Long Baseline Array concluded that Andromeda would definitely hit the Milky Way, potentially even in a head-on encounter that would devastate both spiral structures. A subsequent study published in 2019 incorporated data from the Gaia spacecraft and found the encounter was more likely to be a glancing blow rather than a direct hit, but still concluded that collision was certain. The predicted timescale was 4.5 billion years, conveniently occurring after the Sun had already begun evolving into a red giant and rendering Earth uninhabitable. However, revolutionary research led by Tilsawala at the University of Helsinki and published in June 2025 in the journal Nature Astronomy has completely upended this picture. By carefully analyzing uncertainties in measurements of galaxy positions, velocities and masses, and by incorporating the gravitational influence of other nearby galaxies that previous studies had ignored or underestimated, astronomers discovered that the fate of the Milky Way remains entirely open. The probability of collision within the next 10 billion years may be only about 50%. This represents a dramatic shift from the near certainty of earlier predictions. The likelihood of collision within the next 5 billion years drops to less than 2%. If a merger does occur, it is more probable to happen around 7 to 8 billion years from now, rather than the previously predicted 4 to 5 billion years. The research team considered 22 different variables and ran 100,000 computer simulations to trace the evolution of the local group over the next 10 billion years. These simulations incorporated the latest data from both the Gaia spacecraft, which has measured the positions and motions of more than 1 billion stars, and the Hubble Space Telescope, which can measure the sideways motion of galaxies across the sky with extraordinary precision. The team also used updated estimates of galactic masses derived from observations of stellar motions, gas distributions, and gravitational effects on smaller satellite galaxies. What emerged from this massive computational effort was surprising. In approximately half of the simulations, the Milky Way and Andromeda fly past each other during their first close approach, missing each other completely on the initial pass. Then, over billions of years, mutual gravitational attraction pulls them back together, and they eventually collide during a second or even third pericenter passage, perhaps 7 to 8 billion years from now. But in the other half of simulations, the two galaxies escape each other entirely, at least for the next 10 billion years. They pass by, then continue moving apart, never to merge within the observable future. The key to understanding this uncertainty lies in two additional galaxies that play crucial but opposite roles in the cosmic drama. The Triangulum Galaxy, also known as Messier 33, is the third largest member of the local group and orbits near Andromeda. It has approximately half the mass of either the Milky Way or Andromeda, and is currently located about 3 million light-years from Earth. When simulations include the Triangulum Galaxy, the merger probability between the Milky Way and Andromeda increases. The Triangulum Galaxy's gravity nudges Andromeda toward the Milky Way, increasing the likelihood of collision. Working against this effect is the Large Magellanic Cloud, a satellite galaxy of the Milky Way visible from the southern hemisphere as a faint smudge of light. The Large Magellanic Cloud has a mass of perhaps 10 billion solar masses and orbits the Milky Way on a path that runs perpendicular to the Milky Way Andromeda orbit. This perpendicular motion is crucial. As the Large Magellanic Cloud orbits, it pulls the Milky Way up and away from the plane in which Andromeda approaches, decreasing the collision likelihood. Like a cosmic hero, the Large Magellanic Cloud tugs us towards safety, though it cannot guarantee our escape. The research team predicts that a merger between the Milky Way and the Large Magellanic Cloud is almost inevitable within the next 2 billion years, occurring well before any potential collision with Andromeda. If the collision with Andromeda does occur, stars will mostly not collide due to vast distances between them. This might seem counterintuitive, given that we are talking about a collision between galaxies containing hundreds of billions of stars each, but galaxies are mostly empty space. Even though each galaxy contains hundreds of billions of stars, those stars are separated by enormous distances, measured in light years. The average distance between stars in the solar neighborhood is several light years, while stars themselves are typically only a few million miles across. When the two galaxies interpenetrate, individual stars will pass by each other like ships in the night, their vast separation ensuring that direct stellar collisions remain extraordinarily rare. Computer simulations tracking millions of individual stellar orbits show that the chance of our Sun colliding with another star during the merger is virtually zero, perhaps 1 in a trillion. However, while stars will not collide, the overall structure of both galaxies will be dramatically and irreversibly altered by gravitational interactions. The orderly disk structures that have persisted for billions of years will be shredded and reorganized over the course of the merger. The spiral arms will distort dramatically, and star formation will increase to rates not seen in billions of years. As the two galaxies pass through each other, their gravitational fields will pull on gas clouds throughout both systems. These tidal forces will compress the gas, triggering intense bursts of star formation, unlike anything the galaxies have experienced since their youth. The night sky, assuming Earth still has observers capable of appreciating it, will blaze with newly formed stars, their blue-white light illuminating regions of space that were once dark. Massive stars with tens or even hundreds of times the mass of the Sun will live fast and die young, exploding as supernovae within a few million years of their birth. Each explosion will briefly outshine the entire galaxy, releasing as much energy in seconds as the Sun will produce, over its entire 10 billion year lifetime. The orderly spiral structure of both galaxies will be destroyed, replaced by chaotic streams of stars pulled into long tidal tails, extending hundreds of thousands of light years into intergalactic space. These tidal tails, visible in computer simulations and observed in merging galaxies throughout the universe, are the gravitational equivalent of ocean tides raised by the moon on Earth, but on a scale almost impossible to comprehend. After the initial encounter, the galaxies will swing apart, then fall back together under mutual gravitational attraction. This cosmic dance will repeat several times, perhaps 3 or 4 close passes, over approximately 2 billion years until the two galaxies finally merge completely, forming a single giant elliptical galaxy that astronomers have nicknamed Milkomeda or Milkdromeda. The two supermassive black holes at the centers of each galaxy will eventually spiral together and merge, releasing gravitational waves that ripple across the universe, carrying energy equivalent to the annihilation of several solar masses. The solar system may be pushed into a new orbit far from the galactic center. Computer simulations that track the motion of individual stars during galactic mergers show that stars initially located in the disk like our Sun can be flung to much more distant orbits. Instead of residing 26,000 light-years from the galactic center as we do today, the Sun might end up 50,000 light-years or more from the core of the new merged galaxy. This would place us in the sparse outskirts of Milkomeda, far from the central regions where most stars will congregate. The night sky from Earth, assuming the planet survives the Sun's red giant phase, which will occur before any potential collision, will look completely different from any vantage point in human history. The dense stellar populations near the galactic center will appear as a bright glow dominating one portion of the sky, but individual stars visible to the naked eye will be fewer and more scattered than they are today. Paradoxically, despite living in a galaxy with twice as many stars as either the Milky Way or Andromeda contain today, the night sky might appear less crowded with stars because those stars will be distributed across a much larger volume. The solar system itself will remain intact throughout this cosmic upheaval. The gravitational binding between the Sun and its planets operates on scales of astronomical units, and this binding is far stronger than the tidal forces exerted by passing stars or the overall galactic gravitational field operating on scales of thousands of light years. Constellations will change over millions of years, even before any collision occurs. The stars that form familiar patterns like Orion the Hunter, the Big Dipper, Cassiopeia the Queen, and the Southern Cross are not gravitationally bound to each other. They simply happen to lie in roughly the same direction as seen from Earth, but they are at vastly different distances and moving in different directions through space at different speeds. Over tens of thousands of years, these individual motions become noticeable even to careful observers. Stars drift across the sky relative to each other, slowly distorting the shapes of constellations that have guided human navigation and mythology for thousands of years. In 100,000 years, the Big Dipper will no longer look like a dipper. The handle will bend, and the bowl will flatten into an unrecognizable shape. The bright star Arcturus, currently racing through the galaxy at high speed, will have moved to a completely different part of the sky. In 1 million years, virtually all constellations will be completely unrecognizable. The stars we see today will have moved to entirely different positions in the sky, and the patterns our ancestors used to tell stories and mark the seasons will be lost forever. This process continues regardless of any galactic merger, driven by the individual orbital motions of stars traveling on slightly different paths around the galaxy at slightly different speeds. The familiar patterns we use to navigate the night sky are temporary, existing only for brief moments in cosmic time, snapshots of an ever-changing stellar landscape. Modern mapping efforts, particularly the Gaia mission, are revolutionizing Milky Way research with measurements of more than 1 billion stars. Launched by the European Space Agency in 2013, Gaia orbits the Sun at a distance of 1.5 million kilometers from Earth, positioned at the Lagrange point 2, where gravitational forces from the Sun and Earth balance, allowing the spacecraft to maintain a stable position with minimal fuel expenditure. From this vantage point, it measures the positions of stars with unprecedented precision, detecting shifts as small as a few millionths of an arcsecond. To appreciate this precision, imagine measuring the diameter of a human hair from 1,000 kilometers away, or spotting a coin on the surface of the Moon from Earth. Gaia also measures stellar motions across the sky, called proper motions, and determines distances using parallax, the apparent shift in a star's position when viewed from different points in Earth's orbit around the Sun. By combining position, distance, and motion data for each star, astronomers can reconstruct the three-dimensional structure of the galaxy and trace how stars move through it over millions of years, essentially creating a time-lapse movie of galactic evolution. Each Gaia data release has transformed our understanding of galactic structure, revealing warps, streams, ripples, and other features invisible to previous surveys that sampled only a tiny fraction of the galaxy's stellar population. The mission has discovered hundreds of thousands of previously unknown stars, mapped the spiral arms in unprecedented detail, traced the debris of ancient galactic collisions that occurred billions of years ago, and provided the data necessary to question the inevitability of the Milky Way Andromeda collision. Understanding the Milky Way connects us to the vast cosmic processes that created everything we see around us and everything we are made of. The Milky Way is the stage on which the drama of our existence unfolds. Every star in the night sky tells part of this story. We are citizens of a vast cosmic metropolis, residents of a barred spiral galaxy 13.6 billion years old, 100,000 light-years across, home to 200 billion stars, and possibly destined for a grand collision billions of years hence. This is our cosmic address, our place in the universe, and understanding it is one of the great achievements of human intellect.